Can you? Yes, thank you then. Okay, so I wrote down here a very brief reminder of what I was talking about yesterday. So let me say it very quickly. So the whole point was that I defined this thing I called the Brownian scattering transform. And it was defined as follows. So the first thing was to define this operator. So you can think of it either as an operator or as an integral kernel. And what it does is that you're asking for the probability, so it's better in the picture. You start a Brownian motion at U1, you let it run, and you ask, what's the probability that it's going to hit the hypograph of this upper semi-continuous function and exit at L at position U2? Okay? And I call that this hit probability. And then there's this strange, well, maybe not so strange, so it's just a solution operator of a certain system of PDEs, which is what I wrote yesterday. And it turns out that if you take this hit operator and you surround it by ST minus L and ST minus L adjoint on the other side, then you can actually take a limit. And we spent the last part of the lecture yesterday more or less seeing how that works. So essentially, it's just a simple computation in terms of the composition of this hitting probability. But then the nice thing is that even though taking a limit when L goes to infinity of this makes no sense, since here we're sort of applying the backwards hit kernel that in a way undoes that Brownian motion in a certain way. But the nice thing is that this is only for t positive. Having this third derivative part here actually allows us to make sense of everything. And I should say something. So this e to the t d cubed, it's really not, so we saw this yesterday, but it's not so mysterious. So really, e to the t thirds d cubed uv, this is nothing but the Ayyer function of u minus v. So that's an integral. Sorry, not with a t. I should put a 1. So 1/3 d cubed, that's really just this Ayyer transform kernel. Okay? But it's just easier to write it this way, and it's sort of, this is the way in which it's going to arise from TASEP very clearly, and we will see that probably on Friday. And yeah, this is really what's going on. Okay, so then we saw, so out of this limit, which I showed you why it exists, of course, one has to show that the limit exists. I didn't do that yesterday, but you can, that's not really in the notes, but you can go check the paper. So one can make sense of this, one gets this Brownian scattering transform, and then what I'm calling the KPZ fixed point kernel, which is simply what goes inside the formula for the KPZ fixed point distribution, is given as a conjugation by these hit kernels of the Brownian scattering transform. And again, the reason why I can conjugate, in general, this makes no sense if x is positive, but I can do it because if you notice, this is acting outside. So if I look at this definition, this e to the minus x d squared is really acting on these s's here. And that's allowed. So it's as if I wrote, I'm going to raise this later, but this guy with the x can be defined simply as taking this here and putting a minus x there and a plus x there. Because it's just acting outside. So that's what it means. It's just notationally simpler to write things this way. Okay. So let me show you a corollary of all this. Corollary, so this is going to be a corollary really of the main theorem, which of course we haven't proved, of this convergence to the KPZ fixed point process. And the corollary is the following, is that, okay, what's going on here? I'm given an upper semi-continuous function, and out of that I build this operator, which sort of tells me what's the probability that a Brownian motion starting from minus infinity is going to hit the hypograph on the whole line. So the way to think about it is, I start a Brownian motion at minus infinity, I let it run, I let it exit at plus infinity in some asymptotic way, and I ask what's the probability that that's going to hit the hypograph. And it turns out that if I'm now only given k, and I don't know what's h, I can recover h out of this scattering operator. So I can do this inversion. So that's the corollary. So the mapping, and I'm going to prove it. It's one line. So the mapping that takes a function in UC, and to it associates, let's say, this family of operators, because there's a parameter t, but you should notice that t it's just a simple parameter outside. So really, I have to write t because otherwise this makes no sense as written. But t is not really playing any role. As long as t is positive, you can make sense of this limit. And if I give you the operator for some time t, you can very easily tell me what's the operator at some other time. I just have to compose with the right e to the 1/3 td cubed, so that it's basically because of the semigroup property of that. So essentially, you could think of this as saying the mapping which to h in UC associates just the scattering operator can be inverted. Meaning, if you give me k, I tell you who is h. So this is a sort of inverse problem. And the proof, well, it's actually, this is the proof. So I'm going to compute the limit. Okay, this is almost the proof, but it's essentially the proof. I'm going to compute the limit of this determinant as t goes to 0. Okay, I have these things for all t, so I can take this limit. That doesn't tell me that the limit exists, but I can try it. Well, but this is just the probability starting from h0 that my fixed point process at time t, position x, is going to be less than a. Okay, but as t goes to 0, h of t becomes simply h of 0. So this limit actually equals, so the limit equals the indicator function that h naught of x is less than x, is less than a. So I take the limit as t goes to 0 of this determinant, and that tells me if h0 of x is less than a. Well, but I can do that for every x and for every a, and therefore I know what's h0. Okay, so this works for every x a. So you're done. Okay, so this is sort of a nice corollary, which in principle has nothing to do with KPZ. It's just I construct this operator, and I can reconstruct, if you give me the operator, I can reconstruct h. Questions? You look like you have a question. Okay, so the determinant equals this. And this is the theorem. I mean, this is the main theorem. This is a corollary of the theorem. Okay? But I'm starting with h0. h0 here is deterministic. And t is going to 0. Okay, so I have to show that actually there's some continuity. But as t goes to 0, well, this just goes to the initial condition. So I'm looking at the probability that this deterministic function is below a. Well, that's 1 if it is below a, 0 otherwise. Yes, I need that continuity.
Can you see the direct from the determinant? Just make operation with a, then it goes to the
That's a good question. And I don't know how to do that, but I think it can be done. I can do it. Okay, so I really haven't tried this. So it's bound to be a little bit complicated. There's an analog version, there's an analog formula for TASEP. And for that one, it can be done. I can do it directly. So Leandro's question is, can I see this convergence without using this equality? Just take the determinant, take t to 0, and try to check that you get this indicator function. If I use the TASEP version, I know how to do it. If I use this KPZ fixed point version, so the asymptotic version, I'm not sure. I haven't really tried it. Because I know it's a bit more complicated, but it should be possible. But it's not necessary. Yes, exactly. So the kernel is, you can think of it as an operator. So fix t, because as I said, having one t or some other t doesn't make any difference. So you give me this for some t. It's an operator in L2, acting on L2. Or if you want, not even, it's a function of two variables, right? Because I think of these operators as integral operators with some kernel. So you give me this function of two variables, and this function of two variables, what it's telling you, sort of vaguely, is what's the probability that a Brownian motion starting at -infinity, going to +infinity, starting at u1, ending at u2, in quotes of course, because I'm going from -infinity to infinity, hits the epigraph. And if I just tell you all those probabilities for every u1 and every u2, I can tell you who's the... It's a sort of scattering problem. That's one reason why, for the name, for this Brownian scattering operator. So I'm sort of sending this information from -infinity, seeing what happens at +infinity, and sort of scattering off this hypograph. And now I only give you that information, I can recover it. Okay, this is just a nice corollary, but it's not part of the main story, but it's somehow appealing, I think. Okay. So, as I said, I would tell you today how to get the Ayyer processes. This is actually simple. So let's recover them. The Ayyer processes. Not all of them. I can't quite recover the stationary ones, or not all of them, but the Ayyer 1 and the Ayyer 2 processes, and also the Ayyer 2 to 1 process, if you know what that is, can be done. So let's first think of the case. So the first case is what's called the narrow wedge initial condition. So this corresponds to TASEP with step initial condition. So if you remember, this meant that was the TASEP initial condition, right? So this means H, let me put a superscript TASEP here. So the initial condition for TASEP is simply minus the absolute value of x. And now what you do is you rescale this diffusively in the way we've been doing. And when you do that, it's very easy to see that this wedge, as you take epsilon to 0, it starts getting narrower and narrower and narrower and narrower and narrower. So in the end, what you get is that H TASEP rescaled, that's the notation I was using yesterday, it goes to the following function, as epsilon goes to 0. So it goes to 0 when x equals 0, and it goes to -infinity when x is not 0. It's just because it's doing this. And as I was saying yesterday, that's a nice upper semi-continuous function. It's in the space of functions we allow. Okay, so I'll call this thing, let's call it this, narrow wedge sub 0. In the notes I have a different name, but it's It's a German font, so it's hard to do on the board. Okay, so that's my initial condition. Now I need to compute this operator, because that's going to tell me what's the process. So we have to compute this heat probability. Okay? But here's what we're doing. So I'm going from minus L to L. Okay? And my function is 0 here, and minus infinity everywhere else. And now I'm not going to compute this yet, I'm only going to compute this heat probability. I'm supposed to compute what? I'm supposed to compute the probability that I start from some point over here, I end at some other point over there, and I have to hit the hypograph of this function. Well, but it's very easy what has to happen. There's only one way in which I can hit the hypograph of that function. I can only hit it at the origin, I mean at time 0, and I just have to go below 0 times 0. It's the only way, because this thing is minus infinity everywhere else. You see that? So if I want to hit the hypograph of this function, the hypograph of that function is just this red set. So I have to hit that. It's the only way. So P of heat, a narrow wedge at 0, minus LL. Well, let's write it like this. Starting at U, ending at V. This is just, well, you can just write it as follows. It's the integral from minus infinity to 0 of d eta, let's say, of the Brownian transition probability starting at U, ending at eta, and then the Brownian transition probability, which is this heat kernel, starting at eta and ending at V. So in my picture, that's eta. Okay, this is really completely straightforward. But now look, what happens when I apply ST minus L and ST minus L on both sides? Okay, so then ST minus L adjoint P heat is narrow wedge ST L UV equals, well, the ST minus L on the left just goes inside and applies to this guy. So I get integral from minus infinity to 0 d eta, and then this is nothing but S0 L. Remember that when L is positive, so this is allowed, even if t equals 0. No, it's inside it's L. Oh, yes, thank you. So when I compose this with that, I get ST U eta, and then I get star T V eta. And sorry, I'm missing here a 0, so it's ST comma 0. That's the point. Okay, because I get L and minus L. And if I now set T equals 1, I just told you that when I put a 1 and there's no heat kernel part, this is just an Airy function. So you write it down, and this thing is integral from minus infinity to 0 d eta Airy U minus eta Airy V minus eta. This is exactly the Airy kernel that I wrote the other day. It's literally the Airy kernel. So probably on Monday I wrote it U plus eta, V plus eta with the integral from 0 to infinity, but of course that's the same. And this is the kernel that appears. That's what I showed you for the Airy 2 process. Okay? So this tells me that if I compute the fixed point process with a narrow wedge initial condition, then this has to be the Airy 2 process minus a problem. I'm only doing 1 point, but then the extended kernel is going to be equal to the extended kernel, and everything works out. Is it clear? Match. Yeah, so you just match this to the earlier formula, and you see that it is what it should be. Okay, so how about flat? So flat, I will do it quickly because it's only slightly more complicated, but there's some estimates that need to be done. So for flat, the take-up initial data looks like this. And H epsilon goes to 0. Yeah, this thing is just getting flattened, and you just get 0. So now, when I compute this hit probability, I'm asking what's the probability that I'm going to hit that region. That's the hypograph of 0. Okay? So now that there's, okay, this one is a little bit different because, of course, if I start below 0, I already hit. Or if I end below 0, I already hit. The interesting part is what happens if I start above and end above. And then you're computing this probability of doing something like this. And the reflection principle tells you that this is the same as computing the probability of going from here to there. That's just the usual reflection principle for Brownian motion, right? So if U1, U2 are positive, then what you get is that this hit probability, P hit 0 minus L, L, so I'll write UV like before, UV this equals exactly, I'm going to write it just, so there's a little bit more detail in the notes, I think. So I'm going to use the reflection principle, so, okay, it should be the transition probability for a Brownian motion on an interval 2L going from U to minus V. That's the reflection principle, okay? And I can write that as follows, e to the L Laplacian, rho naught, e to the L Laplacian d squared, uv, where this is just the reflection operator, so rho applied to some function gives me f of minus x. This is just because the reflection and the heat kernel, they commute. And now you see what happens. So I'm still in the case where u and v are positive, but let me pretend that this works for all u and v, which it does not, but let me pretend that for a moment. So now I'm going to apply this SL on the left, SL on the right, and this is going to disappear again. And essentially, I'm going to get an Airy function here, an Airy function there, just like in the previous case, with a reflection in the middle. Now, that's what happens, again, if I assume that u and v are positive, which is not the case. But one can show that if I use this formula for all u and v, I'm making an error, but that error goes to 0 as I take that limit. So essentially, what happens if I start or end below in the limit won't matter. It goes to 0 after I do this operation. So after doing all this, what you get is that k times 1 of hit 0 of u comma v, this equals the integral from minus infinity to infinity. So this one, here I had the integral from minus infinity to 0 because of that projection here. But now I'm just applying the reflection principle and getting this reflection in the middle, so I get this area, sorry, the eta area of U plus eta, sorry, area, well, it doesn't matter, I can do either, V plus eta. So one of them is reflected. What that rho 0 is doing here is it's changing the sign of that eta. And actually this is a known object. There's an Airy function identity which tells you that this is 2 to the minus 1/3 area of 2 to the minus 1/3 U plus V. And then if you remember in the first lecture, I told you, I think I missed the 2 to the thirds, but I told you that the kernel that appears for the area 1 process is exactly area of U plus V, modulo these constants. Okay, so this tells me that the fixed point process at time 1, x, started with initial condition 0, is just the area 1 process. Okay. So these are the two easy cases. There's another easy case, which is this half flat initial condition, which means that I put flat here and minus infinity there, and you do exactly the same computation. And well, it's slightly more complicated, but not very much. And you get something called the area 2-to-1 process, which is exactly what it should be. So at least in these cases, we can get the old results. In the other cases, except for the stationary case, which is what I said that we can't do, but in the other cases, there's no explicit formula, so there's nothing to compare with. But we do have this formula. And for instance, every time, so if you have an H for which there is an explicit heating time distribution formula for a Brownian motion, then you have a completely explicit, complicated maybe, but explicit formula. Yes? To do some, sorry. If you do two sharp wedges, then you're going to get a formula. It's explicit because then, okay, if you want to hit two sharp wedges like this, and then minus infinity here, and you start from here, say from here and go there, well, there's two possibilities. You either go below this or below that. So you get a sum of these things. So it's the sum of the probability of going below there plus the probability of going below there minus the probability of the intersection. And it's going to be explicit. And if you wanted to do, so that's going to be a nice, so this is going to be pretty simple. It's going to be a sum or a sum of three things. And you can compute, sure. And you could use it for something. I mean, if there's something one wants to compute about it, that one is going to be simple. Yes? That's not that I know. Okay, beta equals 1, beta equals 2. Yes. If you want to do beta equals 4, you would need to, so that's known to happen when you take like half space processes. But if you want to do beta in general, not that I know of. I would guess the answer is no, but who knows? So the only the classical cases have arose in these problems in general. So there has been no connection with the general ones, as far as I know. Okay. So as I was saying, if H is sort of nice, then you get these nice formulas. If H is not so nice, or it's general, you still have a formula. It's in terms of some heating times. But what I'm going to show you next, and this is not in the course notes, this is something new, is that you can still use general H without knowing anything about the heating times to say something interesting. So the kernel it looks complicated, but actually it has enough structure that one is able to do computations and say interesting things. Is there any other question before that? Because I'm going to switch slightly. Okay, so let me try to motivate what I'm going to say. So what I want to talk about now is the question of integrability. So TASEP and all these other models have been long known, and this is the reason why we can do things, to have some integrable structure. You have exact formulas, and it has connections with integrable systems, okay? If you don't know what that is, it doesn't matter, but it has nice connections with deterministic systems for which you have lots of formulas and nice structure. So there's, one can ask the question of whether there's some integrable model or some sort of integrability behind this KPZ fixed point. So just to motivate, okay, let me first, I'm going to define, let FTXR be the probability starting at H0, and here H0, it's going to be, you want, well, okay, it's going to be any initial condition in UC, so the probability that this fixed point process at time t, space x, is less than r. So just the distribution function, but it depends on three variables, t, x, and r. Okay? And H0, an arbitrary UC function. So what we just saw is the following. We just saw that if I look at time 1, I'm going to fix x equals 0, just for simplicity, and any r, then this is the Tracy-Widom GUE distribution if H0 is the narrow wedge initial condition. That's what we showed over there, because the marginals of the area 2 process are GUE, and that's actually, it gives you exactly the Fresnel determinant formula for this distribution. And this is the GOE distribution. You get a factor in front, but it's just because of those 2 to the thirds. If H0 is flat. That's what we just saw. Now, many people here will know, if you have studied some random matrix theory, that these two distributions can be written in terms of the solution of the Hastings-MacLeod solution, as in terms of the Hastings-MacLeod solution of the pi-Levet-2 equation. Okay? So let me say that. These two functions have expressions in terms of the Hastings solution of the pi-Levet-2 equation. What's the pi-Levet-2 equation? I think okay, some marks over there. So this is the equation Q double prime of R equals, and I'm going to get wrong the factors. It's better to, yeah, so it's x, okay, QR of x equals x, Q of x plus 2q cubed x. So that's the ODE. And this is, so the Hastings-MacLeod solution is the one such that Q of x behaves like area of x as x goes to infinity. So this is a very famous function. It comes from integrable systems. And so, for instance, FGUE of R equals, if I remember correctly, it equals that. Okay, so you take this famous equation, you solve it with this boundary condition, you put it in here, and out pops the GUE distribution. This is Tracy and Widom 94. And there's a similar formula for, again in terms of Q, for the GOE case. So Okay, a natural question is, so there's sort of two natural questions here. Number one, how on earth does this play a role in this KPZ fixed point? I mean, it somehow should be hidden there, because somehow the ARE2 process is a fundamental solution of all this, and it's given, the marginals are given in terms of the pi level 2 equation. So somehow it should show up. But number two, can I write something sort of like that in some way for the full function? Okay? And it turns out that you can. So I'm going to write the theorem. I'm not going to prove it. This theorem is proved just by using the explicit, the Freedom determinant formula. If someone is interested, I can tell you more or less what it uses. But it's just a long computation. So theorem, this is in progress. So this is with Jeremy, but it hasn't been posted yet. So it says the following: let phi of t x r be the second derivative of the logarithm of f. And now I'm going to write a PDE for phi. Then okay, I'm running out of space. This is a nice equation, so I'm going to give myself some space. Plus, there's all these factors, but that's just from scaling. Plus 1/4 dx squared phi equals 0. So this thing satisfies this equation, and actually, so I don't think many of you have seen this equation, maybe some of you, but this is known as the KP equation. This is the Kadomtsev-Petviashvili 2 equation. It's a famous equation. It's another integrable system. It's a sort of two-dimensional extension of the KdV equation. So KdV is this equation that it's giving you, it's a one-dimensional equation modeling water waves in shallow waters. And this is a sort of two-dimensional extension where you have an additional variable, and the wave sort of depends slowly on that transverse direction. So this is the KP2 equations. The two, don't worry about the two. It has to do with the sign of one of the constants here. So this is Kadomtsev-Petviashvili. And yeah, there it is. So now if you want to know how this probability evolves, well, you take the log, you take the derivative, you solve this thing, and out pops the evolution. Now, if you don't like this equation, there's at least one version which is simpler. So if I take the flat case, then so go back to this fixed point process, or think about TASEP. The dynamics is translation invariant, and my initial condition is translation invariant, which means that the solution has to be translation invariant. And hence, f will not depend on x. Right? I'll start with a translation invariant initial condition. So f should not depend on x. But if f does not depend on x, then phi does not depend on x. It means that this is gone. And then, well, you can show that you can remove this dr. You just integrate and show that the constant that you get is 0. And you get this equation. Just that, ftx. And that's just the KdV equation. So actually, for flat initial condition, this distribution function satisfies KdV. Okay, so let me write that. If H0 equals 0, then F does not depend on X, and then phi satisfies dt phi plus this is just the usual KdV equation. Okay? And so what, as I said, I won't say anything about the proof, but maybe just one point about the proof is that the initial condition, of course here the initial condition is playing a role because of what I just said, but here the initial condition plays for the dynamics of the PDE. Of course the initial condition is going to show up in the initial condition of the PDE, but except for that, the initial condition plays absolutely no role in the proof. So, and even this scattering operator is playing just scantily a role. So really all you're using is this fact that you have this STX on one side and STX on the other side, and exploiting that, one can get the formula. That's a very good question. I have no idea. So, no, so actually the name, we put that name much before discovering this. And it's actually, I should explain that where the name comes from. So it's a sort of scattering, it's like an inverse scattering problem. So what's going on, so I'm making a little aside, is that, so if you know some inverse scattering theory, what you do, say actually for KdV, what you're mentioning, is that you want to solve KdV, and what you do is you map this to a completely different problem about a certain Schrodinger operator, and that's a linear problem for some different object. So you map it to this object, you run this linear evolution, which is much simpler, of course, than that nonlinear PDE. You get the solution at time t, and then you have to invert, right? That's what the inverse scattering method does. And what we're doing here, not here, but in this fixed point formula, it's very similar. It's sort of conceptually similar. You start with the initial condition H0, you map it to this Brownian scattering operator. Now you evolve this, so the Brownian scattering operator, think about it at time 0, which is putting t equals 0, okay? Now you evolve it in time up to time t. That evolution is linear, one can check. It's very simple, it satisfies a linear PDE. And then what you have to do at time t, now I sort of map it back by doing this sort of inverse scattering and trying to recover the condition. So that's where the name comes from. What's the relation with the inverse scattering transform for KdV? I don't know. It's a good idea. This is really, it's a good question, I mean. This is really new, so we haven't looked at that. Okay. So I said that if one looks at this, then there's sort of two natural questions that come into mind, at least. So one was, can I do something similar? And the answer is yes, that's the answer. And the other question was, well, what do the Tracy-Widom distributions have to do with this? So there's a sort of natural question in the field, which is somehow these Tracy-Widom distributions should be the self-invariant solutions of something, which is what usually happens with these fixed point objects. And it turns out that it is the case. So this is what's giving you the Pi-Levé. So from here you can see, if you look for invariant solutions of this, I'm going to explain what I mean, you do get Pi-Levé. So let me show you how. So now, I'm going to use that. I'm going to use that. I'm going to use it right now. Yes, exactly. But for this proof, I am not using that at all. It's completely general. In the particular case, I can do something. So let me show you what I'll do. So Kp is, okay, so this fixed point process is 1, 2, 3 scaling invariant. It means that this f function has to have that 1, 2, 3 scaling. So if this is the equation that's governing that, then it should also satisfy the same scaling. And it's true. I mean, I just gave you a proof, but you can also check it directly. So Kp is 1, 2, 3 scaling invariant, i.e. invariant under the following mapping. So I take phi of tr txr, and I'm going to map it to alpha to the minus 2 phi of alpha to the minus 3t, alpha to the minus 2x, alpha to the minus 1r. And I also have to scale the initial condition. So if I scale the initial condition like this, alpha to the minus 1, h0 alpha squared of x. So if I do that to the equation, so now forget about this fixed point. I just take this PDE and I make these replacements. I get back the same solution. This is something you can check. Okay, so that's the first piece of information. It has to be the case because it comes from this 1, 2, 3 scaling invariant object. But again, you can just check it from the PDE. Now, if I take narrow wedge initial condition, the narrow wedge initial condition is itself invariant under diffusive scaling. Why do I have to use diffusive? Because the initial condition doesn't see the 3. Right? Because the time is not a part of the initial condition. So narrow wedge is invariant under diffusive scaling. Okay? And as Leandro was saying, I have one more piece of information about narrow wedge. I know exactly how it depends on x, right? Because I just erased it, but I know that h in that case looks like, okay, there's going to be some t's, but let's forget about the t's for now. It looks like Airy2 minus a parabola. The Airy2 process, it's a stationary process. It has the same distribution everywhere, but I have to shift by this parabola. But I can use that. I mean, I can just sort of add the parabola back in. Okay, so let's say narrow wedge is invariant under diffusive scaling, and we know x only comes in as a parabolic shift. So why am I saying all this? Because if you notice that, then you would see that it makes sense to ask the following thing. So let me say, so it is natural to look for self-invariant solutions, or scaling invariant solutions. Sorry, I meant. Solutions of the form. So this is going to be the. So I'm going to look for a solution phi of t r r of the following form. So here you have to make some choice. So I'm going to make my choice equals minus t to the 2/3. So this t to the 2/3 is sort of the alpha squared, or the alpha to the minus 2. Yeah, the alpha to the minus 2 times some function psi of t to the minus 1/3 r, and I'm going to add back in the parabola. So why do I do this? Because this object that I put here has the right scaling invariance, and since I added back the parabola, I should expect that it actually only sort of depends on, the dependence on x is gone. So the point would be that if I do this, I should expect that if I translate the PDE for phi into a PDE for psi, it's actually only going to be an ODE. It's only going to depend on the whole variable. And that actually works out. So plugging in, we get the following. So I won't do it, but it's an exercise. So you get psi triple prime of r minus 12 psi of r psi prime of r. This is not very important, but minus 4r psi prime of r minus 2 psi of r equals 0. So in this nice case where I have scaling invariance and stationarity, I can turn my PDE into an ODE. It's a third order ODE. Here comes the magic. And this goes back to the work of, I actually don't know exactly the reference. I guess Miura might be one of them. But this is from the 60s, I think. Essentially tells us that one should try the following guess. So if one puts psi of r equals minus q of r squared, then q solves by level 2. You can check. And this q squared here is exactly this q squared there. It's exactly the same thing. So if I take this and I take the log and I differentiate twice, I get q squared, minus q squared. So you see what's going on. How does the Tracy-Williams distribution, at least this one, arise? And what's the natural way to explain it is that this is solving the KP equation, and the right scaling invariant solution of the KP equation is actually given by Levet in this way. Okay? So this was for narrow wedge, and for flat, similar thing works for flat. So one does exactly the same thing, except that for flat, I don't have to add any parabola because the thing is already stationary. So you do it. When you do it, you only do it here because this term is not there. You do the same game, and what you get is, well, you have to do a slightly different transform, but again, you get the Pi-Levet 2 equation. It's not what I'm saying. It's calculus, but it's not completely straightforward. The least straightforward part is to see. It's to guess that this is what you should do. Notice that this is a third order ODE, and Pi-Levet 2 is a second order ODE. So somehow this transform gets rid of the third order part and gives you a second order ODE. But there it is. I mean, that's one way to understand how these Tracy-Williams distributions arise. Finite dimensional distributions? Very good question. You want to know what happens when I take several x's. Work in progress. So so for now we have something, but it's not as appealing as this. We're trying to work out if we get something better. I can tell you later, but I don't have a nice complete answer yet. So when the same techniques apply, but really what's going on is that, really the hard part of this, it doesn't end up being very hard in the end when you do the computation, but the thing that should be complicated to deal with, of course, is this non-linearity. This equation is not linear, and this is the non-linear part. And so the trick is that, really the way this works is that this is given by a determinant, and when I differentiate the log of a determinant, I get a trace. So really, this is an equation for a certain trace. And then I get the trace of something times the trace of some other thing, and I have a trace of something and a trace of some other thing, and then everything else is traces. And what I would like to sort of is to put everything inside one single trace. So you have to somehow linearize that product. That is not hard to do in the one-dimensional case, and it seems to be much harder when you have these extended kernels. So yes, that's sort of in progress. Any other questions? Oh, you have to. Well, you just get them because you know that the finite dimension. You know that this is GUE anyway. So you just use the tails that you know from the. Right? I mean, because you know that this is going to decay like e to the minus 4/3 r to the 3/2. When you differentiate, that doesn't change. So you take a log, and well, it works out. So this is not only pi 2, it's actually the right Hastings-MacLeod solution of pi 2. So I have 4 minutes left. Yeah, I think I'm going to stop here because what I wanted to do next, but I only got to this point, is to start talking about TASEP again. So, and that's what I'm going to do in the next 2 lectures. I'm going to try to explain how one actually gets to this formula, which is behind all these things. So we're going to have to go back to TASEP. And I'm going to explain the basic ideas behind the proof and how one gets a solution, what should become apparent at the end is where this STX comes from and where this Brownian heating problem comes from. So that's going to come very naturally from the solution that we get for TASEP. So the strategy again is we're going to give an explicit formula for TASEP. There were explicit formulas for TASEP before, but they were not completely explicit or not useful. So the strategy is to get a formula which is useful, and the formula is going to be given as the determinant of I minus a certain operator k in little L2 of z instead of L2 of r. Or really, it's going to be L2 of z plus or something like that. It's a half interval. It's analog to what we have, and this guy here is going to be completely analog to the fixed point kernel, except that instead of having this STX, you're going to have some discrete thing, and a certain random walk heating probability is going to show up, which is going to give you this Brownian heating probability in the end. But yeah, I have to explain where that comes from. And if I have time, so I'll do that on tomorrow and probably all of Friday or part of Friday. And if I have time at the end of Friday, I'm going to show you the proofs of some of the properties that one can prove out of this formula. Okay, but that's it for today.